So the HotI panels are the bread and butter of this conference, okay? So this is the moment where we have some lively discussions with the best experts in the world. So this is one of the reasons so many people come to this conference, just because it's a unique opportunity to listen directly from the, I would say, horse mouth of the network designers, what is their point of view. So the title of this panel is EtherNet versus EtherNOT again. So the again, because this debate has been going on now for at least a couple of decades. And spoiler alert, it never ends up very well for EtherNOT, okay? If you look at this from an historical point of view, but maybe things are different. And today we have some of the best experts in the world that will be, commenting on this topic. So specifically, we have Darius from LightMatter, and Brad from Intel, Larry from Nvidia, Frank from AMD, and Torsten from ETH, Zurich, and Microsoft. Okay. So the way we plan to organize this panel is that we will go in alphabetical order. We start with Darius, then Brad, and then Larry, Frank, and Torsten. And everybody will be given about 10 minutes ballpark to introduce himself and present his position. And this will lead to about an hour. And then after that, we'll open the floor to questions, and we will discuss this question from the audience. Okay, this is a format that has been very successful in the past. So we are trying to follow the footsteps of what we did in the previous years. So, and this is maybe as a motivator. So there is this paper that made some waves lately about the Internet Consortium, and then this the established network in the AI Center, which is NVLink. So this is obviously two fields that will be expanded and discussed during this panel. Now, without further ado, I will pass the token to Darius and for the first presentation.
Yeah, thanks so much for the intro, Fabrizio. I'm going to grab the screen. All right. That should work.
It works.
All right. Before I jump right into the question that you proposed, Fabrizio, I'm going to take this opportunity to introduce our company, as we may not be a household name just yet. We're a small company of about 125 employees. I'm one of the 3 founders of the company. We're backed by some of the most forward-thinking investors on the planet today. That includes Sequoia Capital, GV, Spark Capital, Matrix Partners, Viking Global, Fidelity, and HPE. We have 2 major offices in both coasts, in Boston as well as in Mountain View. So Passage is one of our product. It is our photonic interconnect product. It's a wafer scale photonic interconnect. Enables heterogeneous chiplets to be connected by high-speed optical links that are made out of silicon waveguides. Now, these waveguides use multiple wavelengths to support high bandwidth. And it also features built-in optical circuit switch, where connection topology between the chiplets can be reprogrammed during runtime. And I think this product is what puts us on the map, that a lot of people notice this product. And in terms of Passage, we can go from a few reticles to even an entire wafer, about 200 millimeters to 200 millimeters. And Nick, our CEO, is actually going to reveal more details about Passage tomorrow at his keynote. So going back to the question that Fabrizio proposed, Ethernet or EtherNOT. My view is that Ethernet will always be useful for compatibility for heterogeneous systems, but today it has limitations. And we're faced with this opportunity to rethink about our basic assumptions of how we interconnect our computes together, our interconnect architecture. And that's driven by AI and ML that needs high bandwidth and low latency interconnect. Well, the good news is that optics can be the physical layer that drives both Ethernet and any new interconnect that we can come up with. Some very important features of optical links. This first feature is around its high bandwidth. It's inherently high bandwidth because it uses carrier signals that are in the hundreds of terahertz regime. This enables wavelength division multiplexing, such as shown in that figure, where we can increase the bandwidth of a single optical fiber or a single optical waveguide by just using multiple colors. So signals of different wavelengths can be multiplexed together into that one optical channel. And generally, if you use n different wavelengths, then the bandwidth of that optical link can be increased by n times, barring any crosstalk. And optical links also have low latency. Links are typically limited by their time of flight, and optical links can have longer reach, where standard optical fibers typically have losses in the order of 0.3 dB per kilometer. That's a pretty impressive number. So the low losses means that optical links have higher SNR than electronic links that can give us better error rate performance in the link. So with lower errors, this means that we can either get rid of forward error correction or FEC entirely, or use a lighter FEC protocol. And that way we can reduce the number of clock cycles or latency that are spent on forward error correction. Lower error rate also means that we can reduce retransmission that can really bottleneck the network. Optics also enable interconnection at massive scale, where tens of thousands to more than 100,000 compute elements can be connected together. And last but not least, optical technologies today are quite mature in the sense that we can actually perform optical circuit switching natively with solid state circuits. This has been thought about for quite some time, and it was also brought up a couple times today. So Passage is doing this natively using its solid state switches, and the connection topology between the compute elements can be reconfigured during runtime. And that topology should be determined by the application itself. So what is the best topology for that application? And it can be especially powerful if combined with electronic packet switching. So the bottom line, I think there's a big opportunity here. I think many experts are in agreement that we should reevaluate the use of Ethernet for AI and machine learning and other HPC workloads. This gives us the opportunity to co-design an entire compute platform, starting from the large-scale systems down to the small physical layers. But this time, we can do it with networking and security as a first-class citizen in the whole co-design effort. So Ethernet or EtherNOT, I would say we need both, and optics can help with both. This is a saying from someone within our company. School buses are for highway, and F1 cars are for the track. You need both of them, so you should optimize both of them at the infrastructure level, but they can't do each other's job. So I think we need both Ethernet and EtherNOT.
Okay. Thanks. So I think, Brad, you can move forward.
Perfect. Get my slides up. Can everybody see that?
Yes, it is.
All right. Hey, thanks for having me, guys. My name is Brad Burres. Just by way of introduction, I'm a senior fellow at Intel, where I work in our network and edge group. I've been at Intel for a while. I've been there 26 years. I currently lead our architecture team that spans our traditional NICs, our IPU, or what many people call DPU products, as well as our Ethernet IPs that go into our other SoCs. And then beyond that, my past work, I've led a bunch of data center SoCs, including our first one used in the data center and the first use of Atom or the E-core in the data center. I've led a converged PCH for Atom Xeon, and I've led a bunch of accelerator things across a variety of domains, as well as I started in networking domain, working on the XP family of processors for anybody who's been around that long. Then I got my undergrad at University of Arizona and my master's at WPI. So that's me in a nutshell. All right, so let's jump in. So I just wanted to kind of set some background because I do think there are lots of networks when we talk about this, and the conversation was really around accelerator networks, but in this case, the dominant accelerator really is AI, which is dominating the conversation today. And so really there's three networks you should talk about when you're talking about these accelerator networks. There's if you think about a box of a bunch of accelerators working together, we talk about this as that scale up domain. So it's usually within one physical box. It's a smaller number of nodes anyways. Then as you want to grow your node count, you go out to something we call the scale out network. And so this is how you get more and more and more of these things. So you can grow from say the scale up domain is is it 8, is it 16, is it 256, something on that scale. The scale out network in AI today is going to go up to 20,000 and go bigger, right? So that you can get to a lot more accelerators through that scale out network. And then there's a third network, which we typically call the front end network, and this is sort of your standard Ethernet network in the data center, and that's where you get to storage. That's where the tenant workloads are running, things like that. And so, at least I took the Ethernet versus EtherNOT discussion to talk about these first two, and so that's what I'm going to talk about: the scale up versus scale out. And so, at least from my perspective, I see scale out networking as moving towards Ethernet. So today it is a mix of probably dominated by InfiniBand, but with Ethernet sort of moving into position. And the reason we're seeing this growth in Ethernet has really driven from the cloud service providers, who have really been pushing Ethernet performance and TCO. And so I think the reason non-Ethernet networks made a lot of sense for scale out in the past was their requirements were different, right? It was being driven by the highest end HPC type of installs in these private installations that were really pushing, speeds and feeds faster and really cared more about latency and things like that. And so, there was a need for a non-Ethernet network. And what we're seeing in this day and age is that, those assumptions are no longer true, right? That Ethernet is, pivoting to higher speeds, right? We're starting to deploy 400 gig and going fast to 800 gig quickly. We see, switches evolving to have, be much more optimized for domain-specific uses. So it's not just sort of your standard Ethernet switch at the top of rack or at somewhere in your class, but it's, domain-specific capabilities that you can have that it can be targeted for lower latency, can be targeted for, even some of these things like network offloads that you might want to do. And beyond that, if you assume, cloud service providers or, some of the biggest customers in the world are deploying Ethernet as the main network, you have all these other problems you have to solve. If you create a new network, you have to have a way to manage it. You have to be able to orchestrate your resources. You have to have, cost-effective cabling. Everybody wants vendor diversity, and all of that really, as Ethernet catches up on speeds and feeds, really gets you to provide a lot of momentum for Ethernet to fit into the scale out domain. And on top of it, there's an opportunity. I don't know if this is, I think the verdict on this one materializing at least soon is sort of out, but you have this potential to converge that front end network I talked about with your scale out networks, and you could have a single common fabric, and you wouldn't necessarily need to have them completely physically isolated like I showed in that previous picture. And that has a lot of upsides if you're able to do that in the future in terms of absolute cost of deployment. All right, so I guess there's the view on scale out, should move to Ethernet. Scale up, I think, is a pretty different statement, or at least it's much less clear. And that's because the requirements are pretty different, right? The node to node bandwidth within that scale up domain is high, and so you really need to come up with a networking technology that can satisfy that scale out requirement. And so that may lead you to say, let me design something a little bit more optimized. But the challenge with that is where scale up starts and where scale up stops and where scale out starts is not super clear, right? Like, today the common deployment for scale out is probably 8 GPUs. it looks like it's growing. Is it going to grow to 16? Is it going to grow to 32? Where do the models going to take it? Is it going to go to 256 or 1K? Like, how do you know what those future workloads bring? And so there is some consternation, I would say, on trying to partition between these two types of networks. And that really leaves you with sort of two architectural directions to head. The first one is to architect your scale-up fabric to be large enough in scale to cover those future model directions. Do I need to support 1K of nodes in my scale-up fabric or not? Or do I just align on I'm going to never grow past 256, right? And this is what we see today with NVLink, right? I think they've talked about up to 256 nodes, and I'm sure someone at Nvidia is thinking about going bigger. And this is clearly a really valid way to go about it. The other thing you can do, and that we see other places in the industry, is you could just work towards converging your scale up and your scaling out solutions. So, put it all on Ethernet and then work on tuning the protocol so that you can, have the, satisfy sort of the latency needs of scale up and the low cost hardware costs, while still being able to flexibly design, how many of the links I put down go for scale out and which ones go by scale up. And this is what Intel has done with their Habana product. The Gaudi series of AI accelerators, and there's other people in the industry doing this as well. Both are valid, both are sort of, I think that this is really where the primary debate is between those two today. And I think, if you look at what is better, I think it's clear you can make both paths work, right? There is some key features we have to be sensitive to, right? Like the NVLink style sort of optimized scale up is better for certain things like, native load store architectures. But, you can make that work in Ethernet by, either bridging between the two or encapsulating it, just load store over Ethernet, so that there's things there to be done. Whereas multi-tenancy, again, that can be made to work on NVLink, but it's already natively designed and managed and sort of invented for Ethernet and works much better. And that's a key feature you'll need. Because if you build a 20,000 node or 100,000 node GPU cluster, you're really going to want to be able to partition that across your customers that are paying. Other key characteristics you need is, your average and, more importantly, long tail latency. So you've got to figure out how to manage that. This is probably one of the big advantages that InfiniBand and NVLink have had, and so we're seeing new transport protocols emerging. We've worked on something in our IPU line with Google that we've been calling reliable transport. You've seen the emergence of the Ultra Ethernet Consortium, which is working on solving these exact problems. And so you see these protocols coming that'll run on Ethernet. And there's other needs coming too, right? As you build these out in CSPs, you're going to need more security, you're going to need more telemetry and all of that. So both can be made to work. But at the end of the day, once you get these technical problems solved, it seems like cost is going to be king. I don't think it's there yet. We've been really working on just getting something that works. But I think pretty quickly, as we've seen this explosion of AI and the investments that have to be made, things will turn into cost. And so that means you need to build something that is cost effective. And that means cost effective in terms of silicon. So you need something with a really small silicon footprint because you have a lot of links you want to drive. You're going to need affordable switches. You're going to need commodity cables. You're going to need things that are low power, right? And so this is going to be what drives the winner of this debate. Going to the question, the reason Ethernet seems to win in the past has always been its TCO model has always evolved to be better than the thing it was competing against. So my prediction here is, independent of whether it's a new dedicated scale up network or Ethernet, you do need it needs to be open. I think one of the things we need to do here is to drive these costs down is to have this ecosystem growing and scaling and people using the same technology, so you get that economy of scale, and so you get portable software that moves across them. And then if you have an open ecosystem, the question is which one is it? And my prediction is I think it's a little bit unwritten, but in my mind Ethernet, we see these protocols emerging. I mentioned those two with UEC and with the reliable transport, so unless you get another open standard emerging, I think it'll be Ethernet, but there are some other ones that could emerge, and CXL is one that comes to mind. So that would be my view. Thank you.
Okay, Brad, thanks for the strategic and the holistic view of the problem. So, Larry, the spotlight is on you now. I can see the presentation. Maybe you are muted. Presentation is okay. Just
okay, here we go. I had to find the unmute button. Thank you. Okay, so hi, I'm Larry Dennison. I'm Director of Network Research at Nvidia. I've been in Nvidia roughly 10 years. I work for Bill Daly, so a lot of the story is going to sound very similar because I work for Bill. In full disclosure, I got my degrees from MIT, and Bill was my thesis advisor back in the early 90s. So I've had a lot of Bill Daly exposure through my life, and we kind of think alike on networking terms. Some of the things that I've been doing at NVIDIA, it's kind of interesting to think. When I first started NVIDIA, I would go to a conference or something and say, I work at NVIDIA, and they go, NVIDIA who? A couple of years later, we started working on networking for GPUs in earnest. You go to a conference and say, hi, I'm interested in these sort of EtherNOT networks, the networks for GPUs, and everybody go, what are you going to do with that anyway? But here we are, in 2023, and NVIDIA, most people know what we do, and they know about the GPU network side of the house. So it's really, really fun. Along the way, my team started looking at the interconnect. We did the initial architecture for like NV switch, the concept for that. Along the way, we did things like the virtual address translation concepts, and also the things for the in-network collectives that became known as SHARP. So we've got some experience there with this GPU NOT side of the house, just kind of pushing ahead on the GPU accelerator interconnect. So that's me. The usual disclaimer, this is my opinion, it's not NVIDIA's opinion, and the data in the slides may or may not be accurate. Just use it for directional purposes, please. Okay. So when Fabrizio asked the question about EtherNOT, that usually you need a couple of business drivers before you come into a new technology. It has to be a big enough market. The reason why Ethernet keeps winning over HPC fabrics is the HPC fabric market was never big. And the question is there a market there which wants this technology, which is big enough to sustain it? The other thing is, what's the gap in features and performance? Can Ethernet actually kind of catch up or meet the things that we're looking for? And as everybody's pointed out, cost efficiency is going to become king. So we have to pay attention there. Okay. When we first started looking at the AI or the GPU networking side, started running some numbers, around 5 years ago, and I keep doing this for fun, and saying, okay, let's take a look at some numbers. How many transceivers are going to be shipped in 2024 at the 400 gig range? The answer was around 8 million. This came from Omni at the OFC forum earlier in the year. 8 million sounds like a lot of transceivers. And then we start looking at our implementations, and we start counting up the transceivers just in the scale out fabric, which is normally around 2 transceivers per GPU, not the data center connectivity. Like, oh, wait, every 100,000 GPUs, we would need around 2.5% of the worldwide transceiver market. Well, I can't tell you how many GPUs we're selling, but I think that number's a little low. And then we start looking at it, and over time, if we start pushing the optics closer to the GPUs, as Bill alluded to, going down to the GPU, that number should go up by a factor of 10. And so you start seeing, just even on the transceiver market space, fairly significant intake just for these accelerated AI systems. And then you start looking over at the switching side, which is the other component, and say, how much bandwidth going for these? Well, GPUs today, 3.2 terabits per second injection bandwidth. Our 800K GPUs would equal the bandwidth supplied by that new oncoming bandwidth from those transceivers. Just people bought transceivers to go on completely new switches. I'm like, that's an interesting number. That says that basically our NVLink switches or NV switches comparable capacity-wise to most of the Ethernet switches for the high-end market, which is a way of saying there is a market big enough. If it can support Ethernet, it certainly can support an EtherNOT network. Okay, as Bill said earlier today, everything in these networks is coming from communication patterns. We have data parallelism and model parallelism, and model parallelism is split into two domains, one of which is the tensor model parallelism area, and the second is the pipeline parallelism area. What this forms are really the communication patterns that go onto the network. During tensor parallelism, we have a lot of exchange of parameters intimately between GPUs. As was spoken about earlier, how many GPUs do we need in a tightly connected domain? It's coming from this tensor parallelism. And as the models are growing, what we're discovering is we just need more GPUs applied in that area, and that domain is growing. The other sides, then, we have the two dimensions of extending the model for LLMs across multiple such clusters, which is the pipeline parallel dimension. But there, it's pretty much a neighbor-to-neighbor communication. It's sending the data down a pipeline. The pipeline is often like 600 or so deep. Think about it as just a large linear structure going up and down. Data parallelism is where we see a lot of the in-network collectives, but it's running a direction that's orthogonal to the pipeline direction. It results in interesting communication patterns. But these are pretty ubiquitous. If you're going in and you're training some other model types, et cetera, these are all pretty foundational concepts, and we're not seeing very much deviation. This is at odds what we saw with HPC, or depending on what you're doing, say adaptive mesh communication patterns were either their nearest neighbor or there was something else. Very difficult to map. Here, it's very clean and very well understood up front. This results in sort of this three dimensions of communication. Communication patterns, the intensity for the local model parallelism, the cluster of GPUs. We've got the pipeline parallel dimension and the also the data parallel dimensions. And immediately your mind goes and said, oh, this network topology really wants to be a torus. And this is kind of Google's insight, where they've been driving the TPUs and their scale outs, but we're not quite sure if it's an n-dimensional torus or what it really should look like. It might be equivalent to flattened butterflies for these large language models. But I want to really point out here is that the application for efficiency at very high bandwidths needs to cost optimize this. And this does not look like a spanning tree. So one of the first immediate things is how do you fit these sorts of models with interesting corners and turns onto a network topology that isn't, it wants to be tree-based. We need more graph-like structures. So some of the desiderata that we're seeing, and I'm just going to kind of step through these because these are the gaps, if you will, between an Ethernet type network and what we require for the AI workloads, the in-network computes, the multicast and collectives. One thing that wasn't mentioned is these have to be source-specific multicast trees. So we have low latency. We can't just go to root a tree and broadcast down. Latency will kill us. These have to be parallel network interfaces. Coming out of the GPUs, you're looking at order 10 terabits network capacity. You're fighting against all the other GPU designers because they want to put compute and memory resources on the same chip. So you have to have a minimalistic NIC interface, and it has to be NIC-less. We can't plunk down an HCA or your traditional Ethernet NIC on a PCIe bus. It will kill us. We can't afford it. Bandwidths are too low. Latency is too high. So you have to go NIC-less, and that's also saying be very careful with those protocol extensions for congestion management, et cetera, has to be minimalistic. The other thing we're observing is the electrical signaling speeds hitting the end of the tail of the curve. Look at directional speed on a single diff pair. 200 gig is around a meter. People are looking at heroics. Maybe we'll see 400 gig per second electrical, but hard to tell. Our circuits guys are going, it's getting really iffy. The CMOS transistors aren't getting better. So for the co-integration of the IOs on the main ASIC, We're already hearing from people about the need for separate I/O dialects because at like 2 nanometer processes can't really fit the I/Os or with the I/O voltages. So again, we're seeing optical as essential. Total bandwidth per fiber is going to be there. When you couple that with the electrical signaling speeds, the rate you want to modulate a lambda, et cetera, you're asking yourself, we're better off optimizing the overall optical plan for one of these AI systems rather than saying, it's got to be 400 gig. No, we're going to pack it all in there. It might be 650 for all we care, but we just need the bandwidth because we're concerned about cost efficiency. The other aspect is fine-grained resiliency. When we look at the bandwidth per fiber or things, we're going to be packing multiple data links in there because dominant failures are still lasers at these reaches. And we need mechanisms that allow us to do the isolation. We haven't seen EtherNet now provide lane failover or graceful degradation from an 800 gig link, say, down to a 600 gig link. But we need in our AI systems because, frankly, if a server goes out when you're running a large training job, the entire training job, 10,000 GPUs or more, has to checkpoint and restart and be reloaded onto another part of the system. It's just the way it is. And so we can't afford to lose resources without providing adequate resiliency. Optical circuit switching is coming. Our friends at Google are showing this again with the TPU. Again, they're remapping things to do job by job planning. Topology is going to follow the communication demands, and it's going to be changing. You can't have you can't have a tree, can't have a spanning tree. It's going to look more like IP, ECMP-based, multi-path routing, non-minimal routing, all the things Bill mentioned earlier. You need to bolt that in there. Massive scale. Ethernet is still flat address space. When you get up to 128K, table updates take a long time. We just need to go deal with some of those things and re-engineer them in the EtherNOT network. Link error correction, FEC is always on. Can't turn it off. Link level retry is very important, including things like selective retry and retry over link aggregates. We have large numbers of link bundles between our switches. If we lose a link, we'd like to have local retry off over an alternative link, things that Ethernet just doesn't provide today. Again, resiliency. We have to minimize the hits, the job interruption time. Hard faults, say less than 2% bandwidth loss after you restore the network. But we also need fast restoration times. Routing restoration, say under 50 milliseconds, both unicast and the multicast trees. And traffic engineering or rebalance, say within 5 seconds. So there's some other characteristics here that are important when we're doing jobs running in a data center that we just need. Congestion management's one of them, tenant mapping, security, encryption, all those things start coming into play. And what I wind up saying to myself is, okay, if we fix all these things in Ethernet, is it still Ethernet? And when would we see it? So I personally think there's a big market out there for EtherNOT. I don't think Ethernet goes away. I think that in the next few years that Ethernet can't move fast enough to address the needs of this market. So thank you. That's my presentation.
Thanks, Larry. This set the perfect stage for Frank and Torsten coming next, okay? Thanks for the great presentation. And Frank, now it's you.
Perfect, thank you. Yeah, I'm Frank Helms. I'm the staff architect for the data center GPU business at AMD. I've been a system architect for a couple decades. Previous life, I was the mobile system architect for about a decade at AMD, culminating in we acquired ATI and did the Future is Fusion, where we integrated CPU and GPU on the same SoC to improve battery life. Then I took a little detour for a few years and went to Samsung and worked on ARM server SoC and learned a whole bunch of stuff there, but obviously no money to be made in ARM server SoC last decade. Looked around, found myself back at AMD. 2014, I got on the GPU train, if you will, and started learning about HPC and machine learning. And I don't know if you go to OCP, there's some talk where you'll probably see like a bunch of history of AMD that I might talk about there. but at any rate, obviously the focus over the past several years has been machine learning for me, GPU-based machine learning. Really appreciate the intro that both Brad and Larry provided. I won't bore you with trying to go through all that. They both covered it very well. Thank you very much, guys. Appreciate that. So I'm going to up-level what I have to say here. Not going to share slides per se, but Ethernet for AI cluster interconnect, of course. Everyone is going to benefit from an open multi-vendor ecosystem enabling competition and choice. I mean, flat out, period, the end. The analogy, easy analogy is the automotive industry. What the heck? Competition improves quality, capability, diversity of options. I mean, I don't have to go too far, but I mean, there are SUVs today that outperform, sports cars, supercars, hypercars from the 80s. So, competition is good. And it's gonna continue to drive to, to the best for the whole entire industry and effectively humanity, because they're the beneficiaries of all this. So, yeah, of course, Ethernet for AI cluster interconnect. I will say that AMD is absolutely interested in open competition, open options, choice, et cetera. And so that is a key tenet. So we're not trying to be exclusive on, what an interconnect is. So of course, Ethernet, and whatever else people want to do. Let me give a few examples from our current GPU product. Sorry, not trying to make a plug here, but AMD MI250 GPUs. If you just go look at the supercomputing top 500 list, what you'll find is number one on that list over an exaflop is Frontier at Oak Ridge National Labs. And guess what? Slingshot 11. It's an Ethernet-based interconnect, okay, some enhancements on top of Ethernet, but it's Ethernet, and it's the highest throughput HPC supercomputer on the planet. Go down the list a little bit, there's Lumi, Euro HPC Center in Finland, same Ethernet, underlying Ethernet interconnect. And Lumi is being used for by the Allen Institute for AI for developing a large open state-of-the-art generative language model, AI2 OLMO, open language model. So at any rate, AMD is in favor of choice. If you go down that list a little bit further, you're going to find number 11. Number 11 on the supercomputing top 500 list is Explorer WUS3, which is an Azure cluster of MI250. So that one uses InfiniBand. Like I said, we're not exclusive here. Choice is good, options are good. The PCIe attached cluster interconnect is working, really well for everyone, and so diversity of choice is good. Different people can make different choices, but anyway, so the bottom line is there is existence proof of very large, high performance clusters that are using Ethernet. Maybe Ethernet with some modifications. I mean, I think if you just look at AWS, their H100 public clusters are, 20,000 GPU superclusters, elastic fabric adapter. I think that's Ethernet plus some enhancements. Yeah, so anyway, just a few examples. So, I mean, one key advantage, and I think this has already been touched on, but, advantage of Ethernet is it's a multi-vendor switch ecosystem, which is really driving TCO improvements. And the thing is that the Ethernet switch radix is super important for improving TCO. Getting a larger number of GPUs under fewer layers of switch is really important for TCO. And so, that's one, I mean, Ethernet's every bit as competitive as anything else in terms of switch radix. Driving up the bandwidth per pin, I think this has been hit on before, but, nothing's driving harder or faster than Ethernet. Maybe the same, but not harder or faster. It's basically 3 times the pin rate of, same day PCIe. So yeah, the CXL PCIe not a compete, precisely because bandwidth per pin is not there. And a whole pile of other things. but that's one of the things you get with Ethernet, right? You've got a multi-vendor ecosystem. They're all driving radix. They're all driving throughput per pin. So those are key ingredients of TCO. And oh, by the way, it's been mentioned multiple times here, research and deployment of co-packaged optics where they make sense. And I mean, yes, eventually it's going to become more, optics is going to become more ubiquitous, no doubt. But it's kind of a stage thing, and you deploy optics where copper fails. Where copper can't do the job, you use optics, and so clearly, large reach between high radix switches in a data center, that's an obvious place for optics. And so I mean, I don't have to talk about the Ethernet vendor stuff; they can talk about it themselves. But clearly, there's public proof points of high radix Ethernet switches with CPO. So I mean, I guess the third thing is, yes, there is the Ultra Ethernet Consortium. Founding members including AMD, Arista, Broadcom, Cisco, Eviden, HPE, Intel, Meta, Microsoft. This is just a small indication that there's a lot of pent-up demand for Ethernet, for cluster interconnect, for large AI, I'll say training clusters anyway, and HPC. By the way, everything I'm saying is my opinion. I'm not trying to be the direct mouth of AMD here. And so that Ethernet consortium is Ultra Ethernet Consortium is trying to put together an architecture so there can be more commonality amongst the various Ethernet switch options, which then makes it easier, lower friction for hyperscalers to have choice. So I mean, I'll just stop and summarize. Maybe I'm using my whole time. I don't know, but so again. Open multi-vendor ecosystem is great for everyone. Competition is good for everyone. Ethernet is being used today for large-scale HPC and machine learning clusters. Ethernet's on the leading edge of switch-based interconnect technology, both in terms of the bandwidth per pin and capabilities that are associated with those switches. Ethernet, Ultra Ethernet Consortium is just one indication of the pent-up demand for it, and I'll stop there. Thanks.
But I was saying we have time. If you wanna.
No, I'm good. Let's let the other folks go, and then we can have whatever panel discussion we got here.
Torsten, best for last. So you have your UEC stand now. Okay.
This is going to be fun. Okay. My mission is now to disagree with everybody on the panel, because I've had the opportunity to listen to everybody, and so now I can go and disagree with everybody. Okay, so I'm Torsten. I'm a professor at ETH Zurich in Switzerland. I've actually been the general chair of HotI 08, I believe, so I have a long history, and great to see Dan and Fabrizio and the guys again. So in my free time, which I have copious of in the summer, I'm helping out Microsoft, but nothing I'm saying here has anything to do that Microsoft would agree to. But behind me is a Microsoft office. Okay. Ethernet, the statements were made, and I don't want to corner Larry too much here, but Ethernet is really the present and future of data centers and supercomputers, and all these reasons have been brought up before, but it's just not the Ethernet as we know it today. It's going to be very different from the Ethernet as we know it today. And even Larry's company is selling Ethernet products, as we know. So there's a Rocky and everything. So basically everybody on the call is agreeing that Ethernet is important, but Ethernet needs evolution. So let's see. But I want to first focus a little bit more on what are we expecting to see in the future in data center and supercomputer workloads. Well, it's really only one thing. And we've heard this so many times. By the way, that image is AI generated. So AI basically advertises itself as the future here. By the way, in my talk, all artwork is AI generated with Microsoft products. So no plug here. But what does it mean to build a cloud AI network? And this is something I want to thank both Bill and Larry for already summarizing these 3 dimensions of parallelism: data parallelism, pipeline parallelism, and what I would call operator parallelism, but they call tensor parallelism, same thing. And here's an animation for this. And you've heard this 3 times now if you watch the keynote, so I don't want to repeat it. But as Larry said, this is actually a 3D torus in some sense, or you could build, you could force the communication into a mode to really be a logical 3D torus. Right? So keep this in mind. So actually, if you didn't follow this, you can watch me giving a talk at Microsoft Research, a full hour about this kind of thing. But again, I don't have enough time here in the 10 minutes to summarize all of this. So I'll just bear with me, assume it's a 3D torus, including all the tricks you can play. This is where the whole hour blah, blah comes in. But now the question is, if I have a 3D toroidal communication pattern, would I be using a fat tree to build it? Of course not. Sorry, Brad. Of course, that is not a great idea. And Bill made a very good point about this. But would I be using a dragonfly? No, of course not. It's for the same reason. So sorry, Larry. Sorry, Bill. Basically the same argument. What would I be using? Well, naturally, I would be using a topology that kind of fits my communication pattern, right? Sounds reasonable, right? So if I have this 3D torus, we all know that we can fold the 3D torus or plane it into multiple pieces into a 2-dimensional topology. So let me now propose something that we've been working on that could fulfill that goal. I personally, and we believe that Google has a very limited way of doing things with a built-out torus, as has been the case in TPU v2, v3, and I believe v4, but I'm not fully sure. But bear with me, we'll get to something more flexible. So let's assume you have an accelerator, and the accelerator needs, let's say, a lot of bandwidth, 1.6 terabit per second today. That's a lot. That's nothing like the 400G link we've heard this morning from Bill and also Larry. Let's assume we need more, because we have, of course, a much more capable accelerator than an Nvidia GPU. So let's talk about the future. So, and we need many links, many lanes coming into this thing. So one potential proposal would be to arrange these links into 2 dimensions, so north, east, south, and west. And then build a little packet switch into the thing. So now we have a 2x2 switch, or basically if it's bidirectional, a 4x4 switch, which is very cheap, I guess we all know, because it scales quadratically, much cheaper than a 32x32 or something switch. Of course, one of those cables is not enough, so you have many of those planes, but the switches don't grow. So now you need many accelerators. What do? You take these accelerators, map them onto a 2x2 board. And those of you who pay attention, you already see, as Bill mentioned this morning, you have very nice. I'm assuming you see my mouse here. Oh no, wait. How do I get to this? To this pointer thing here. Here is the laser pointer. So you can already see that there are many PCB links or potentially interchiplet links that are extremely cheap. If you go back to Bill's slide this morning, so they're basically 2 to 3 orders of magnitude cheaper than any other link you can have. So now if you take these things, of course, a 2x2 board is not what you would call an AI supercomputer. If you take these things and arrange those into a 2-dimensional pattern again, like you now have a second dimension, look at this guy, it's a little bit slow coming up. And you now connect each row and each column of those fully, because if you would fully connect them all together, then you would be back to a fat tree or something like this. But now bear with me that you have just one switch for each row and each column here. And then those of you who are mathematicians, you immediately see, oh, that is a Hamming graph. That's a 2-dimensional Hamming graph. Some of you would be calling that a flattened butterfly, or some of you would be calling that, what's it called? A HyperX topology by HPE. They're basically topologically identical. However, mathematicians win because they've been 100 years earlier with the name of Hamming graph here. So what you could now do is you could build this thing, for example, even with a larger board, like a 4x4 board. You obviously immediately see that you have more links on board, and that thing is getting much cheaper. And then I could be talking a whole lot about this, but I don't have enough time. I just want to give you some numbers here. So here are some topologies. So non-blocking fat tree, 50% taper fat tree, 75% taper fat tree, NVIDIA's favorite dragonfly, the 2-dimensional HyperX topology, which you could also call a flattened butterfly if you want. And then our 2x2 board and a 4x4 board. And as a comparison point, a 2D torus like Google has been building. Just for the cost, for 16,000 accelerators, 1.4 terabit per second today. That's a $680 million endeavor with a non-blocking fat tree. Again, sorry, Brad, it's getting expensive if you do that. So yeah, I know Microsoft said they have like $1 billion to be invested into AI supercomputing, but that's not the budget for the network. That's the budget for the whole thing. So now if you look at the global injection bandwidth, you can immediately see, well, the torus kind of sucks. That's percent of the injection bandwidth. For 16,000 accelerators, you get 1% injection bandwidth. Of course, the non-blocking fat tree, yay, gets you like 100%. Everything else is somewhere in between. If you now look at the cost per injection bandwidth, relative to the non-blocking fat tree, you see everything kind of loses, but the Hemming 4 mesh is actually quite good. But nobody really needs global bandwidth in AI computation. So what really matters is all reduced bandwidth. Funnily, all of those topologies literally get nearly 100% all reduced bandwidth. Easy to explain because all reduced doesn't need a lot of global bandwidth. It suffices to have a tree. But now if you look at the cost per injection, per all reduced bandwidth, you see, well, Dragonfly is kind of okay with 1.6x over fat tree, but actually Hemming mesh is like 14x, so that's like an order of magnitude more. The torus wins, that's 15 times more. However, it really loses a global bandwidth. So basically what this means is that somehow this Hemming mesh topology is a trade-off between a global topology like a fat tree and a local topology like a 2D mesh, and you can adjust the group size and adjust the cost like you want. Okay, I don't want to spend too much time on it. I already did. Fabrizio said we had more time. So let me now get to the real point. And he just unmuted to tell me to shut up. But I'll take...
No, I'm the exact contrary. You're putting gasoline on the fire. Please keep going.
Okay. I want to make sure we have a good discussion afterwards. So now comes a bit more controversy here. So my claim would be cloud and HPC networks are bound to converge, period. Because I know some mega data center providers that are running very large networks. I mean, the scale is unimaginably large. And it's unimaginably expensive, of course, because each piece costs O of 1 money. Sometimes people already forget this. And so the other observation in this field is that cloud AI is an incredible gravity well, because as I mentioned, the future is going to be AI, no matter what you do. And so this means we need to look a little bit more at cloud AI, but also how does it work in the context of these hyperscale things. So last year, some friends of mine and I got together. Actually, that paper was triggered by Hot Interconnects 2012, where I had a discussion with Ariel Hendel. I was in a similar panel with him, and we discussed the same question. I am not kidding. There was a 2012 Hot Interconnects panel like 10 years ago on exactly the same topic. And we came to exactly the same conclusion, but it didn't happen. So but now it'll happen, believe me. So see, I'm already contradicting myself here. And so finally, 10 years later, we wrote this paper. What would it take to converge data center and high performance computing networks? So here we have a guy from Broadcom. By the way, it's too bad that we don't have Broadcom here, because one argument to be made for EtherNet is to quote Ram Velaga, one of the VPs of Broadcom. How many ports are deployed per year in EtherNet? So we've seen Larry's number that I remember in 8,400,000 ports or something like this. Oh no, that was transceivers. So now it's 600 million Ethernet ports. So that's like 4 per year deployed, according to Ram Velaga. So that's like 4 ports for every human born. So I don't know what that number means, but he keeps making these jokes. So not credit to me, but credit to Ram. So we have a whole lot of Ethernet stuff around. So how do we converge these two? It really doesn't make sense to deploy 2 networks. However, you could make multiple arguments, and I don't want to go into details here, why they're separate. So one big argument here is that an HPC network is typically a one-off installation. Like you roll in your computer, it serves its 4 years, and then you throw it in the trash can. While in a data center environment, there is really old stuff in production today in data centers. Like, I'm not kidding, 2 decades old hardware is actually still running, and that is connected via a very compatible, backwards compatible interconnect. So the whole business of AI supercomputers in the cloud is going to move that because AI supercomputers could be rolled in, but that really depends, because it also depends on the operation philosophy. As we mentioned, run to completion jobs like AI training nobody really cares if they crash. I actually completely disagree with the statement made earlier that it's super expensive to restart a job. It's not really. And actually, for data science reasons, these training jobs crash every now and then and need to be restarted because like you need to revert for your mini batch. If you don't believe me, go to the log of Meta. They have trained the OPT model, and you will see it's a mess. They have publicly documented how they trained the model. It's a mess. While in a real data center, you actually need high reliability services. And I could make more of these points like service diversity, protocol stacks and layers, utilization and applications. I don't want to go into detail here, but there are some points that make the convergence a little bit harder. And we make these points in this paper. So if you care, if you want to learn more about how could we converge these networks, I would recommend looking at the paper. Again, I don't have enough time to go into great detail here. We can discuss this on the panel. I just wanted to raise the points where I disagree with people because that's always fun. But what's happening? I mean, these cloud HPC, I mean, cloud data center providers are not stupid. They're after the money. So they already run HPC installations, in fact, today. So if you go to cloud HPC offerings, so you can go and rent HPC installations today on basically everybody's cloud, like AWS, Azure, GCP, and you may not have heard about it, but Oracle running a cloud as well. And some of those just roll in supercomputer equipment. So Azure and both Azure and Oracle, they just deploy supercomputer technology. You can see latency and bandwidth is very much on par with what we have with on-prem deployments, partially even better. So on-prems are just traditional supercomputers or AI machines. Then AWS and AWS and GCP, as we heard, they're using their front-end network. Well, you could now argue that it's much cheaper to run this reliable datagram, but you can also argue that the bandwidth and the latency speak for themselves. So that's now a question whether you need it or not. If you want to know more about this cloud study, I would refer you to another talk because again, I could give a 30-minute talk on that alone. But my postdoc, my former postdoc is much better at this, so you can watch that talk on YouTube if you want. So now coming really into the business of EtherNet. So now we agreed, I think everybody agrees, EtherNet is the future. But Nvidia and many other people have this wonderful thing that's called RDMA over converged Ethernet, short RoCE. Isn't that great? I mean, basically take all the features of InfiniBand and duct tape them on Ethernet headers. Wonderful, if the duct tape holds. Well, you know, unfortunately, the duct tape doesn't always hold. So we actually, from a mega data center provider perspective, have written a little paper that Fabrizio pointed out. There was a huge industry involvement here, talking to various people, trying to identify the pain points of RoCE today. These works actually predated the Ultra Ethernet movement that we've heard about multiple times. And I would claim that they're part of the motivation for some companies to get together to do this. And here, as we've already heard, there's this Ultra Ethernet Consortium, has a wonderful logo, much better, by the way, than the previous names that we had in mind. So founding members we already heard about. I would recommend all of you go read the Ultra Ethernet white paper. It's a wonderful summary of what the real technologies, or what the, not real, but the kind of high-level technologies are that people are talking about, or we are talking about in that context. I just want to use the last 3 minutes maybe to go through a little bit of the pain points that we identified in this paper, to just raise some high-level issues, because I've already seen at least 2 people shaking their head when I said RoCE is not it. So I just want to stir up that discussion that you can attack me. I'll give you some ammunition here to why RoCE is great. So why do we believe that RoCE is a bit of a problem? Well, one problem is lossless transport as implemented with PFC. So basically the converged Ethernet thing really means that we're misusing a feature that was introduced in fast Ethernet, that was also decades ago, to deal with the discrepancy of speed between 10 megabit and 100 megabit ports at the time. PFC was really intended to kind of stop the flow of the port if it was going too fast for my little 10 megabit output port in switch. So it's now used to implement essentially lossless transmission at layer 2 in Ethernet today in order to enable my duct tape RoCE packets to go over that transport. And I mean, first as an engineer, I'm like, well, that sounds wonky. Oh my God. But actually it's working. It's reasonably well. There's one problem with it. You just need headroom buffer, because you need to stop the flow before you're running out of buffers. And then if you look at the switch throughput growing here, so these are the announced products of Broadcom, just because we had such a nice Tomahawk series here. So at 51T, we already need 40 megabyte of buffers in the switch. You need 70 at 100T, and obviously this is going to continue growing. So this is bad. You need lots of buffering. Now the problem is even bigger for a mega data center provider. If you want to run RDMA, lossless RDMA with RoCE and PFC over long links, which some may be doing, you have a problem with your even per port buffer sizes. So if you look at just running it in the same data center, which can be up to a kilometer diameter cabling, you have a requirement of 7 megabyte per port buffer size. If you run it over a region, we're at a gigabyte per port buffer size. So, I mean, that's crazy, obviously, to get full bandwidth. So then we have all these issues that many people know about. I don't want to go into detail here, like head of line blocking caused by PFC, very much an issue, a pain point of lossless networks. Lossless networks, blah, blah, blah. We have go back and retransmission, which is a great pain point for many, many people. We have congestion control with co-located traffic. If I ever put any other traffic on this network, talking about convergence, imagine Zoom now having packets in a lossless network, we would constantly be backed up. Like Bill said this morning, there should never be a packet longer in the network than a microsecond. I completely agree. But hey, then we shouldn't be using PFC and we shouldn't be deploying InfiniBand because these packets can be quite long in the network in InfiniBand. So somehow there must be something cooking in NVIDIA that we don't know about. So there are some header sizes here that are really bad. As I mentioned, RoCE is basically just an InfiniBand BTH duct taped on top of a UDP header. If it's RoCE v2, which is what everybody's deploying. It doesn't really have support for smart stacks. NVIDIA says this themselves. They basically say here, sharp performance advantage over RoCE. You see four times higher performance, so RoCE is not great there. It has tons of security issues, actually tons of them. Read our papers, like my group has published 2 papers at top-class security conferences, how you can crack any RoCE or NVMe system open if you really like. That's just another one. And then there's link level reliability. We heard about FEC being annoying. It remains annoying. The last piece I want to say here is that actually congestion control and load balancing is becoming harder because distances grow, and that's really annoying. So the longer the latency, the higher the BDP, the bandwidth delay product, the longer it takes before I'm actually getting a signal back from the destination. So we need new technologies for dealing with this, basically in network signals and things like this. So this is just a teaser of things that we are looking into. So with that, I would like to conclude. Basically what I said is, well, we want to converge these networks. I was teasing a little bit before that on the topologies. I actually only added those slides while Larry was talking, so I don't have them in the conclusions. So I talked a little bit about this paper here, pain points that may have motivated some companies to go into Ultra Ethernet, talked a little bit about how we look at solutions. There is a summary of how, now you may be saying, well, I didn't present any solutions. Well, yes, because it's still in the definition. If you care about what Ultra Ethernet is doing, here's a little summary of the white paper. Follow me on Twitter if you're interested in more details coming out later maybe. But okay, that's something I don't want to take away right now. Thank you.
Okay, so just to do a little bit of load balancing before opening the floor to questions, I would give a little bit of space to the EtherNOT, given that you guys have been hit so hard from just a question of fairness, if you feel like, okay? If you want, otherwise we can open the floor.
Yeah, just open the floor.
Okay, let's do this. Give me a second. Okay, so let's start from the last question here. Torsten point about checkpoint and node failure. So the question is about the similarities between infrastructure needs and expectation of MPI jobs and AI ML training and the similarities between the two. I mean, obviously, this is a question about Torsten point, but doesn't necessarily a question that Torsten can address first. If anybody wants to talk about the checkpoints needs, feel free.
I'll be happy to, but if somebody else wants.
Okay. Yeah. So, yeah, from our perspective, so what we're currently seeing is that when a job hits one of these critical events, The way the job schedules are currently working is it goes back into the job queue. You don't immediately go find another resource. They have no spare resources. Everything is running flat out, and you wind up being rescheduled. So that's might be okay in certain environments, but there are other ones where training time is important, like the DLRM case, where timeliness of retraining is important to the end customer. You don't want to be re-enqueued. So you're looking at ways of improving the overall reliability of the network. And this is where I'm getting back to, is that, again, you just don't lose one server. You've lost, maybe 10,000 compute hours while you're waiting for your checkpoint restart to do its thing.
Nope.
Okay, go ahead.
So if you lost 10,000 compute hours, then you should checkpoint more often. Right? So that just implies that you either had a 10,000 node job running for an hour without checkpointing. That seems borderline crazy to me, because that is a lot of money.
Well, the cost of your data storage for the backup is also ridiculous.
Well, look. Look at the public meta information of how often their job crashes for data science reasons and does not converge, and they need to restart things anyway without node failures. So if they don't checkpoint at least once every 15 minutes, they're losing too much money. That would be a huge problem. And anybody I know who does.
What you have now is you have to also look at the cost of the time it takes you to do the checkpoint restoration.
Well, which is very, very small. I mean, you have a model. Let's say GPT-3. GPT-3 is 700 gigabyte model in FP32. Right? Agreed. So 700 gigabyte. If I'm running on let's say 10,000 GPUs distributed, I have how many megabytes per GPU to checkpoint? That's nothing.
The issue is not much the training. It's the training data that's been locally loaded. There's an awful lot of, if you will, data that's being also disseminated for the training purposes. So that's also what you're not. That's the other elephant.
Actually, if you guys just
wait,
stop arguing for 1 second on. Well, I'm just saying, if you guys stop ignoring the specific details, I think you agree on the point that we need to make our networks more resilient, right?
Yeah.
I mean, so the nuances of we could argue forever on the numbers we believe in, right? But I think at the end of the day, like it's critical we continue to evolve our technologies, both electrically, protocol-wise, all of it, right, to make the networks more resilient.
No, I promise Fabrizio to disagree here on this panel as much as I can. For AI,
you're doing an excellent job.
I don't think we need to be resilient networks because checkpoint restart is. But actually, let me address the first point that Larry made. So if you have a problem with a scheduler, with node failures, you should fix your scheduler, not your network, because I think that's just a scheduler policy issue that you're running into. If you get to the very end, if you really have critical jobs to execute, you should have a special queue to execute them.
And if you have regularly jobs failing, maybe you need to preserve some capacity, right? I mean, there is ways to manage that.
Exactly.
The current best practices reserve no capacity.
Well, that's a problem with the best
which is great if you're not failing very often, right?
Yeah, well, this is the point, is that, depending on how everything is running, it's all about what is the impact of a failure on your operations, and it varies. I will agree. And everybody just wants to make it better.
So to answer the question, can I just give like 1 minute answer to the question? The answer is pretty much yes. It's very similar to HPC checkpoint restart, but of course it's all different in data sizes, data volume, data management, but otherwise it's very similar.
Okay, I can pass to the next question. So there is a question, a little bit long question on the Tesla transport protocol as a proprietary interconnect. Anyone would like to comment on that?
What was the name of it? Say it again.
Tesla transport protocol. Yeah, it says a 50 gigabyte second TTP protocol link runs over Ethernet to access either a single 400 gigabit Ethernet port or a paired 200 gigabit. I'm not familiar with the.
Yeah, I'm not familiar with it either.
Yeah, it's part of Tesla Dojo, and so the Dojo itself is, it's not the strongest compute node in the world at this point in time, and the network is roughly matched to it. And again, they're training for this is for self-driving cars. And so their model is not the large LLMs. There's a lot of visual processing. Things are fairly node local in many cases. So it's a different critter that they're designing for, is what our observation is. They have aspirations of making it better. It's sort of the first foray. But the same thing, it's like Torsten observed, they have the 2D meshes, they have electrical switches, kind of doing the route through capabilities. It's similar to what you had suggested.
Mm-hmm. And here I would actually agree with you, Larry. So they have a data staging problem, mm-hmm. Because they have very large data. While in large language model training, data is trivial. Loading mm-hmm. a bunch of text files, that's nothing.
Yeah, I guess note to Fabrizio, you should invite someone from Tesla who built the dojo next time. More about that.
If they give us a discount on a car, it will be even better, right?
Oh, I'm in.
We could find nothing written down about what their transport protocol did.
Yeah. That would be curious if the questioner knows anything.
So there is another question about IEEE 800 2.1 has enhanced Ethernet support to TSN, which provides deterministic low latency for applications that need it. It also standardized congestion isolation protocol to fix PFC problems. So I think it is moving in the right direction at a higher rate compared to what is perceived by some panelists. Do you agree?
Yep. It's moving.
It's moving.
I would not claim EtherNet is moving too slow. I'm not sure who said that.
Yeah, I mean, I think there's lots of technologies working on, how do you schedule the wire better? It's not just that one, which is more into the telco kind of 5G side of the world. But there's certainly lots of technologies and lots of investment there, and you're seeing a lot of uses of time across Ethernet.
Okay, then there is another question. Let me see. About Rocky. Rocky is an example of Ethernet which still faces issues today. What are the solutions in Ultra Ethernet or the new Ethernet that addresses the problem faced by Rocky? So fundamentally, what you bring to the table with Ultra Ethernet that is better than Rocky?
They go to me as well, I suppose. Well, we have this white paper, and in the white paper we say multipathing packet spraying, flexible delivery order, modern congestion control, end-to-end telemetry, large-scale stability and reliability, and it also says security. So these are the high-level points that we are bringing, and you could now argue about the details.
So, and then a question which also close to my heart. Can routing in Ethernet networks be evolved to address the needs of AI workloads? Okay, are existing protocols getting in the way, and what higher layer protocol changes, if any, are needed to unblock the new routing techniques for the Ethernet network? Okay, so my understanding is that Ethernet, when you do this type of bulk synchronous all-to-all type of things, is not exactly super happy, right? Whoever wants to take this.
Yeah, I don't think it's super. I'm looking over at the group over here. There's multiple ways, because Torsten buried something in there, which is multipath routing. So the question is, Ultra Ethernet. Talk to me about multipath routing. Come on. It's a fairly change. You've got a big flat address space. What are you going to do?
Well, I think that's right. I don't think routing in general is broken, but I think we have lots of bandwidth through multiple paths through the network that we got to figure out how to take better advantage of. And you can do that today. It's just most things don't. And so, you need protocols like UEC is doing, or like other folks are doing, where you can, spray your packets across, all the various ports, out of the NIC or out of your switch to take advantage of that. And that will solve those problems. So I don't think there's any fundamental limitations to the protocols. But we do have to implement them.
The fun fact here is that 802.1 doesn't really define routing, right? So you could now argue what Ethernet routing even is. And we have these very simple data center style Ethernet routing things where some people are still using Trill and spanning trees and stuff like this, which is a total night. I mean, doesn't make any sense for performance in my view. But you could do that. But then you could also do a slingshot style routing that HPE is doing, and some panelists said this before. It's also Ethernet. So you could actually run extremely advanced adaptive routing on top of Ethernet, and people, I mean, it's not just you can buy a product today that would do it for you. So I don't think Ethernet routing has a problem. We just need to define the right
Ethernet routing.
Excuse me?
Okay, so again, I'm being pedantic here. Is it they've implemented a routing layer over Ethernet frames, or is it really Ethernet routing, or well, have they done the usual, which is, it's an n-bit address, and we just put structure on it, so we have hierarchical addressing and routing and everything else that looks like IP, but we're just going to use the Ethernet MAC address, and we're just not going to tell you it's actually an IP address.
Yeah. We now get into this discussion, what is Ethernet, right? And if you really define Ethernet very strictly as 802.1, then you're stopping at layer 2. So it's just a packet format that defines the MAC layer, the MAC packets. But most people, when they say Ethernet, they kind of mean the stuff on top of it as well. So in some sense, you could now argue.
Usually, when you talk to somebody, you mean IP over Ethernet.
Yeah, let me exactly. This is exactly where I'm getting at. So most people mean the whole stack that sits on top of Ethernet. So I'm subscribing to the most people. So now what you're probably saying is that now, you bring up an example of a proprietary network that's not compatible with anything. But itself, like the HPE network, and say that is Ethernet routing. Well, technically seen, I'm right, but I understand your argument that this may not be what most people think as Ethernet. This is exactly the reason why Ultra Ethernet exists, because we will define a protocol that now a multi-vendor ecosystem like the old Ethernet ecosystem can actually run over. And actually, you guys would be welcome. So
yeah, I mean, I think that's the point of Ultra Ethernet. It's like today
to be open,
I'm not. I mean, I'm AMD. I'm not Broadcom, and again, it's Frank, not AMD. But we probably ought to have somebody from Broadcom or another switch vendor on here to talk about this. But obviously, there are proprietary things laid over Ethernet. Every switch company has something. NIC companies have something. You mentioned the Mount Evans thing with Google. Like, everybody's doing a proprietary way of addressing the issues. And so what we have is we have a multi-vendor ecosystem that has some things that are kind of like, hey, you got to use exactly this NIC, or you got to use exactly these switches, whatever. And the idea with Ultra Ethernet is, hey, like, everybody knows how to address these problems. Let's just say that. And is there a way that we can commonize or get to a common point on how to address these problems with Ethernet? And I think that's the purpose of the Ultra Ethernet Consortium, is all these like-minded folks that have solved these in various ways. Can we come to an agreement on a standardized way so that it's truly interoperable between NICs and switches, and you don't have to have specific NICs or specific switches per se.
Exactly.
I think that we are done with questions. So we are almost at the end of the slot. Any final comments?
What we're just seeing in the AI space, it goes back to the EtherNOT. We looked at all the major startups between Nvidia. You look at Google, who has plenty of experience with EFA. You look at Tesla Dojo. You look at Habana. Everybody's gone Nicholas, and they've got their own network because they needed. In fact, that layer 3 is what's been missing. Okay.
Yep.
Is really the fundamental gap. Now the question is, will Ultra and Ethernet produce something before the market window for it has closed?
The hope is yes.
That's really,
or will it do the same thing that always do, which is there's a subset of people that get aligned a little bit faster, and then standards come out following it. I agree with you there. It's a fundamental question that we got to see is how quickly can we get aligned on what the ecosystem's doing.
Yeah, from our perspective is we need the stuff, we needed it yesterday.
Yep.
We can't wait 3 years for it to be standardized. We have to get it into the pipeline so it can hit 3 years from now. And that means our endpoints, the GPUs, everything else has to be there. And partly why you're seeing the push for EtherNOT is, we're doing pretty well. We had a good earnings call today, for those who hadn't noticed.
Okay.
But the reason is because we needed proprietary technology. We needed it, injected it today. Like with Sharp, we were able to put it in our NICs, our switches, everything else. We weren't waiting for a consortium to define the protocol. So yeah, this is kind of like the tension. There's a big enough market who needs it today, and will we find enough proprietary stuff that you can't address the AI market in time.
But as exactly, completely agreed. I mean, I can speak for every mega data center provider. They have the same problem as you do. I mean, we're the customers in some sense. Yes, yesterday we need the solution. But as Frank and Brad turns out, there are many, many, many solutions you can choose from. And so to be, let's say, mega data center providers, they could be buying from anybody. And this is a problem if it's not a leveled market, because there's a certain vendor lock-in and things like this, as we all understand. And so the interest is really to converge that market. And while we move ahead, we don't want to block anything. Like, everybody moves ahead with their proprietary solutions, but maybe in time X, we will all agree on one. And so we should try to drive that agreement. And if we all agree, it'll be like the EtherNet today that anybody can build, and it's going to be an open market. There will be billions of parts per year deployed. Like, we have 600 million of EtherNet today. And that is the vision. So it doesn't block it. There is no in time in this sense, right? Because today there is business to be done. Tomorrow there is business to be done. In 5 years, there is business to be done. And whenever it hits, it will hit hard, and it will enable this shared market, this shared open ecosystem.
I'm not sure I agree that time doesn't matter. I think it does matter, but otherwise you end up with fractured. Maybe there isn't one, maybe there's three, right? And the more unified we can make it, the better. And so the question is, how do we drive things in that direction quickly? I will say, just to throw Darius a comment, I think in my view, the whole conversation, I think optics is inevitable. I think it's just a matter of when, and it comes down to that cost question. But it seems sort of irrelevant to me on, is it Ethernet or EtherNOT, right? It's going to be whatever wins. It's going to be over optics as soon as optics is cheap enough.
Yeah, I think the question about when optics should be deployed is now. It's right now. I think the technology is matured enough. We got a bunch of new tools that weren't available past 10 years, and we should incorporate that in the new standards.
Yeah, what's also happening is the emergence of the optical circuit switches. The cost of the bandwidth or the bits, the cost of a bit per second on fiber is dropping, which is good. But the number of bits we can pack on a fiber has really caused the amortized price of a port on an OCS to come way down relative to an electrical switch. So you're now looking at a very different network topology. When I'm listening to Torsten, I'm going, great, you're doing all this stuff. Where's your OCSs in this picture? Is Ultra Ethernet willing to say, we're not going to put an Ethernet switch in here. It's just a passive optical circuit switch for the spine. Are you guys willing to do that in your vision?
The topology I talked about, all the global links would be optical in that sense. Because
well, they're optical, but are you using optical circuit switches?
We could be, yes. That wasn't specified.
Amazing, yeah.
Yeah. So if OCS is coming, yes. If you would build it today, maybe not yet. So
actually, Larry, what do you see as the advantage of that? Is it just raw cost? Is it power?
Okay. I guess it's power primarily. To what Torsten said, if you look at the jobs and you look at the communication patterns, if you've got a carefully designed package, you can actually go one hop optical, which is ideal. Yep. You only go there and you never do 2 hops optically. And so you've optimized the cost of your optical plant using the OCSs. And that's really what it's all about. Okay. And so you don't go any indirect or anything else, but that's really the purpose here. And when you start peeling it back, a lot of your problems on security, job isolation, at the scale of the jobs we're running, we're not running a VM on a little x86. we want always 8 GPUs, even in inferencing. I'm sorry, it's a big thing. You bandwidth steer. You're not subdividing the resource. And then you're starting to do, so training inference is going to be completely different. Training looks like fairly large clusters that are your unit of allocation, and OCSs seem to fit very nicely in that, which is what Bill's trying to say. I will disagree a little bit with him on the Dragonfly. I'm agreeing more with Torsten. When you start mapping through the topologies, we're going to discover weird ones that we just have to understand how we map.
Yep.
Oh, I agree.
So,
unexpected.
Yeah. So the question is, how does all that stuff work together? You're talking about Ultra Ethernet. That's part of our vision, is how do we leverage all these things that are coming up?
If you think about Ultra Ethernet, it's just a technology, right? It doesn't talk about topology. Well, and so it just gives you this common understanding of how to run things.
Yeah.
And I think this is really urgently needed, because everybody right now has their own way how to run things, and it's not compatible. That's really the message.
We look at it and say, okay, because right now we have a complete stack. We can go in, annotate the computation graph for the nature of the communication. Is it time urgent? Is it bandwidth sensitive? How do I schedule it? Do I have a synchronization barrier communication here, which requires low tail latency? We can derive all that information direct from the application, provide so many hints to the network that are just not in your Ultra Ethernet standard because they're not thinking AI.
How do you know? That's an interesting, how do you know?
I don't know.
How do you make this statement? Because I was just going to say, hey, we are looking at that, but now you say it's not in. Okay, well,
I don't know. We haven't heard any talk in that direction. So, but the question is, again, if you're
it's almost like NVIDIA should join and help set the direction.
Yeah.
So yeah, but you see what we're saying. Communication is a whole stack problem for AI.
Absolutely.
So we are at the top of our slot. There are a few other questions. I'm sorry, I don't think we have time to go through them. Some of them are very controversial, like what is the best topology? This would be yet another panel, so I don't think we're going to take that today. And I think it's the time for me to pass the token to Dan with the Bubba Memoriam. But before that, I would like to give a big thank and a round of applause to our panelists for their contribution and their open thinking about problems. Let's put it this way. Okay, we had a very good
Thanks,
time.
everyone.
It was a pleasure. Thank
Thank you, everyone.
Guys.
Thank you. So before we adjourn for the day, and before I actually introduce the Head Bubba Memorial cocktail reception, I wanted to say a few words. First of all, thank you to the panel, another outstanding panel. As you said, Fabrizio, this is the bread and butter of Hot Interconnects. We debate these issues. This year is the 30th anniversary of the founding of Hot Interconnects. Started in 2003, and we've had 30 conferences since then. Now it's been 31 years. There was 1 year we didn't have a Hot Interconnects. But I think back on the things we talked about in the mid 90s, they're not all that different from the things we're talking about today. And I was commenting to Bill Daly after his talk that his discussion of buffers reminds me of a huge discussion we had about buffers in 1999 at that Hot Interconnects. And the discussions haven't changed that much, except we know what we're doing and why we're trying to regulate input and output buffers for a much clearer reason and a compelling application. So it's really exciting to see these things. Now, we talk about on this panel Ethernet versus EtherNOT, and someone said, well, what actually is Ethernet? I don't want to give away my age, but I was in the IEEE 802 discussions in the mid-1980s. And to me, Ethernet is two things. It's a frame format and a MAC service interface. And it has survived for all these years because it is only that. By standardizing on those things, we've been able to layer services and new protocols above that MAC service interface. And we've been able to use new technology foundations for implementing the transmission of Ethernet. That served us well. And we can see now that the advancement of copper is certainly giving way to the advancement of fiber as an infrastructure, whether or not you put, Ethernet frames or something else above it. And mostly it's been Ethernet frames. We had these discussions, 20, 25, and 30 years ago, and it was mostly different players. We had MirrorNet, we had some other things that have kind of come and gone. Ethernet has stayed around because it has evolved and adapted. And the reason it could evolve and adapt is because we kept it simple and we didn't try to constrain the physical layer. We didn't try to constrain the protocols that ran above the MAC service interface. So it's a great update on how far Ethernet has come, Fabrizio. So thank you for putting that in the panel. Now, Torsten said, yeah, he was general chair in 2008, and nice to see us again. Hot Interconnects is not just about these technologies. It's about the people that have put this conference together and have come to it and contributed to it for many years. Some dip in and dip out. Some have been here continuously. It's been a real pleasure to see these people and to hear their updated viewpoints on things. And I just find it refreshing every year to hear some new things from old voices as well as from new voices. Now, that brings us to the Head Bubba Memorial Cocktail Reception. When we were in person, which was through 2019, we had an actual reception, and we had, beer and wine and food at the end. And some years we actually had it before the panel, and some years after the panel. And when it was before the panel, we had a very interesting panel discussion. And then it was after the panel, we'd have more just discussion around the tables. And one of the important people in the history of Hot Interconnects is a man named Head Bubba. It was his legal name. He died 10 years ago. But he would come and sort of sit in the back, and he would raise his hand and ask these really uncomfortable questions, because they were really good questions. And he would find the weak points in our argument and the soft spots, and he would bring those to our attention. But he came every year from New York. His position at the time was he was the VP of IT at Credit Suisse, the Swiss bank. He had a hugely important job. And after the 2008 conference that Torsten shared, he invited us to leave Silicon Valley and come to New York and have it there. So in 2009, we went to New York. It's the first time we were not held in Silicon Valley. And he hosted us at the facilities of Credit Suisse. We liked that a lot because previously we'd have been at Stanford, which was complicated. When we came back, we said, we're going to get local companies to host. And we did. Every year, a different company would host us in person. That finally ended. But, and then Head Bubba passed away in 2013 from illness. But we learned a lot from him because he was very pointed and knowledgeable. He didn't take any BS for an answer, and he kept us honest. But he supported the conference. He came every year. He hosted us. He brought the financial community to Hot Interconnects, and he was personally a very generous man with his time, with his hobbies, the things that he had and specialized in, and we appreciated that. So you'll have to go do your own happy hour, but I'm going to raise a glass here of fine wine, which we have in the house because my daughter is a wine in the wine business, and I would just like to raise a toast to all the fine people that have made Hot Interconnects what it is for 30 years, and especially to Head Bubba. Thank you, buddy, for your friendship, for your challenging questions, and for your generosity. We'll see you all tomorrow at 9 a.m. for a fabulous keynote that you're going to hear about from AMD. So thank you for your attendance today. Have a good evening, and we'll see you tomorrow.
Thanks, Dan. Bye.
Bye, everybody.